One type of place where volcanoes form that we haven't really mentioned yet too much is a place called a hotspot. We mentioned them briefly when we were talking about some kind of reference frame for talking about plate motion. But let's talk a little bit more about hotspots now and understand the volcanoes that form above them. Let's imagine that we have a layer of lithosphere, and down here is the asthenosphere. Up here is the lithosphere. Again, with a layer of crust on top of it. Now, one model for explaining hotspot volcanoes, and it's not universally accepted, it's widely accepted, but there's still quite a bit of disagreement about it. But I'll go with it anyway because it's a fairly easy model to understand and it gets some key concepts across. And that is that at depth in the mantle, there are sometimes blobs, columnar-like blobs of hot asthenosphere that rise upward because they're hotter than the surrounding areas and therefore less dense. Remember that when we talk about buoyancy and about materials floating with respect to other materials, what we're saying is that less dense material in a gravitational field will rise above a denser material. So if we have particularly hot mantle at depth, it may have enough buoyancy force to move upwards, flowing very slowly, not as a liquid, but as a solid, just plastically shoving things aside, until it reaches a very shallow level in the earth. This is called a mantle plume. When this mantle plume rises upward, it eventually reaches a shallow level and often will spread out into sort of a mushroom-like head shaped like that. Spreads out like that when it reaches the base of the lithosphere. Well, once again, if you imagine that a volume of rock from great depth is moving upward until it gets to that level, it's undergoing a substantial amount of decompression. And because of that decompression, it starts to melt here. We get partial melting. That forms magma. The magma rises through the lithosphere and erupts at the surface. We call this a hotspot volcano. Where does an example of such a hotspot volcano occur? Well, perhaps the most familiar hotspot volcanoes are the ones of Hawaii. Here's an example of the Hawaiian hotspot chain. The active volcano is on the main island of Hawaii right now. Here's a photograph of one of the more recent eruptions. But all the other volcanoes, all the other islands of Hawaii formed by volcanic activity in the past. How did that happen? Why do you have this succession of progressively older volcanoes as you go off to the northwest? Let's imagine that we represent this plume by orange, and we represent the plate, the lithosphere plate of the Pacific Ocean floor by purple and the overlying layer of gray. Now, over time, that plate moves relative to the mantle plume, or relative to this hotspot, at least according to this hypothesis for how hotspots form. Well, a volcano forms over the plume, but with time, that volcano is carried off of the plume. Finally, when it's no longer on top of the plume, it ceases being active and dies out, and a new volcano forms. It's active for a while, then it too is carried off of the top of the plume until it dies out, and then a new volcano forms, until you develop a whole chain of volcanoes. Now, this arrow here represents the motion of the Pacific Ocean floor. So the hotspot is relatively fixed about where the position of the big island of Hawaii is. As the Pacific plate moves, it carries volcanoes off, and eventually they sink down below the surface of the sea and become underwater mountains called seamounts. What this means is that in the future, eventually the volcanic activity on the big island of Hawaii will cease. It will be carried westward and become a progressively smaller island as it erodes and collapses, and a new volcano will form to the east of that material. So we've now seen how flux melting occurs due to plate tectonics. We've now seen how decompression melting takes place as a consequence of plate tectonics. The final type is heat transfer. And we'll just go back to a couple of our plate settings again. For example, heat transfer melting can take place in a rift because the hot magma that is formed by melting of the asthenosphere is so hot that it can sometimes trigger melting of the surrounding crust in the context of a rift. Similarly, we can have heat transfer melting beneath a convergent plate boundary where the plate is being subducted beneath a continent. And we can also have the same phenomena take place where we have hotspots beneath continents. We can have heat transfer from melts that form in the mantle. When they rise into the crust, they can cause the crust to start to melt. So in conclusion, we can now understand the locations of melting and therefore the locations of volcanoes around the world in the context of plate tectonics theory. We see that in addition, there's a huge amount of volcanic activity taking place on the seafloor along mid-ocean ridges. For example, convergent plate boundary volcanoes occur in the Cascades of northwestern United States, and hotspot volcanoes occur in Hawaii or on Iceland. In addition, there are volcanoes that occur along active rifts, such as along the East African Rift. And finally, there is a lot of unseen volcanic activity that happens along the floor of the ocean in mid-ocean ridges. This occurs around the world and is responsible for producing all of the seafloor that exists on the planet today.